So when we're doing calculations with any of our gas laws, we are assuming that these gases are ideal gases. And two of those assumptions that come up are that the particle size is negligible when you compare it to the size of the container. And the logic there is that if you have a container, it's fairly large. Particles are so small that even though those particles do take up space, they take up such little space compared to the whole container that it's negligible. And the next assumption is that the particle interactions are negligible. So again, even though they might have an attractive repulsive force between them, it's so little in the scheme of things because those particles are moving so quickly that it's negligible. So let's explore these assumptions for a second, and let's talk about something that's at a high pressure. So we've got a gas inside this container. Okay, and our first assumption was that the overall volume of these particles are so small that it doesn't even matter compared to the size of the container. Well, let's explore what would happen if we increase the pressure. And there's two ways we could increase this pressure. We can either add more particles, which would increase the pressure, or we can shrink the container, decrease the volume. So think about what this would look like if we added more particles. So we have the same size container roughly, but this time we're just going to add a tremendous amount of particles. Drawing dots. I'll pause this so you don't have to watch me draw dots. And through the magic of television, all the dots are now drawn. I'm basically Martha Stewart. But if you consider the overall volume of the particles now, I'll keep adding more as I talk, if you keep introducing more and more particles, eventually there's going to be so many particles in here that you can no longer ignore their volume. They will make up a substantial volume of the overall container. Or if we'd had the same amount of atoms of a gas, but you decrease the volume down to a much smaller container, so we have the same number of gas particles in here as in here. Overall, though, the particles' volumes are not negligible anymore because they make up a sizable part of the container's actual volume. So what this does to your calculations is whenever you calculate pressures, or calculate volumes rather, when you're calculating the volume of a gas, if it's under a very high pressure, you're going to get an artificially high volume. And the reason there is the ideal gas law, when you're calculating volume, ignores the volume of these gas particles. But under conditions of very high pressure, you can't ignore the volume of those particles, so they get added to your total volume, and you find that your observed value in the lab is actually higher than the calculated value you get from PV equals nRT. Another situation to think about is very low temperatures. So again, let's say we have a container and we've got some gas particles in it. Now, at room temperature, these particles are moving with enough energy that as they pass one another, they can basically ignore their intermolecular forces. But let's say that we greatly decrease the temperature. So as we decrease the temp, these particles now are moving much more slowly. So whenever they pass one another, there's actually time for those interactions to attract the particles to one another. So at very low temperatures, these intermolecular forces have time to actually attract these molecules together, which pulls them a little bit closer. So what this does is this artificially lowers volume calculations, or artificially lowers actual observed volumes. PV equals nRT ignores these intermolecular forces, so PV equals nRT will show higher volumes than you'll actually observe in real life at low temperatures. Because again, at low temperatures, these intermolecular forces are able to take hold and actually pull each other in, shrinking the volume. And actually, I said volume, but that would assume this is a flexible container. So instead of artificially lowering the volume, since this is a rigid container, let's say this artificially lowers the pressure. That'd make more sense with this given example. If you do PV equals nRT, you should have a calculated pressure. However, in real life, these particles have an opportunity to interact, so you're going to observe a lower pressure than PV equals nRT will give you. So, let's tie this together. You are most likely to have deviations from ideal behavior whenever you are at conditions of high pressure and low temperature. The higher the pressure and the lower the temperature, the less ideal a gas will behave. Another thing to consider is polarity. Polar molecules have greater attraction to one another than nonpolar molecules. So nonpolar molecules will behave less ideally than nonpolar molecules. And again, that's because nonpolar molecules only have dispersion forces interacting between them, whereas polar molecules have dipole-dipole interactions or maybe even hydrogen bonding, and it's harder to ignore those stronger intermolecular forces present in these polar molecules.